Welcome to the deep dive. Today, we are tearing apart the invisible machinery that powers, well, every single piece of digital tech you touch.
Mm-hmm.
From the instant you tap a key on your keyboard to the millisecond, a massive server farm responds. It's all running on these light speed decisions.
And those decisions, they're fundamentally based on the simplest concept imaginable. True or false. That's it.
One or zero.
Exactly. And what we're doing today is revealing the mathematical framework that lets engineers build unbelievably complex digital systems using just those two choices.
So our mission is to take a stack of, let's be honest, pretty dense source material and show you the surprising efficiency gains that are baked into the tools of the trade.
We're talking specifically about Boolean algebra and Karnaugh maps.
Right, and these aren't just, academic exercises. They are the secret weapons used to make circuits faster, smaller, and cheaper.
We should probably start with the core concept, the basic building block.
Combinational circuits.
Yes, and the definition here is absolutely critical. A combinational circuit's outputs are determined only by the logical states of the inputs present right now.
So no memory of the past.
None. No feedback, no internal clock. It is stateless, immediate logic, pure reaction.
Okay, so if we're building a world out of only true and false, we definitely need a language for it. Let's unpack that language of logic. Boolean algebra.
It all starts with the alphabet, Boolean variables, or logic variables.
And they can only hold a value of, what, 0 or 1?
That is it. In the physical world, those binary states are represented by voltage ranges. A high voltage is typically a 1, or true, and a low voltage is 0, is false.
And Boolean algebra is sort of the mathematical bridge, then. It's the process for analyzing and simplifying these zeros and ones.
Exactly. It lets us take a physical logic circuit and express its entire operation with mathematics.
So what are the basic operations?
Well, the basic ones are pretty intuitive. You have A and D, which needs both inputs to be 1.
Okay.
You have OR, which only needs at least one input to be 1. And then you have NOT.
Which just flips it. The logic complement or inversion?
Precisely. But, engineering demands efficiency, so we quickly get other critical functions built from those.
Like NAND and or NOR.
And the conditional operations, exclusive OR, or XOR, and exclusive NOR, XOR.
And all of these abstract math operations, they map directly onto physical hardware components called logic gates?
Yes. A logic gate is really just an electrical circuit, a network of transistors that performs one of these Boolean functions.
And if you're looking at a circuit diagram, you'll see things like the bubble.
Right, that little circle.
What does that signify?
It always signifies a logic inversion is happening right at that point, a NOT operation.
Even those more complex gates are built from the basics. You mentioned the math for the XOR gate. It's written as Y dollars A over line B plus over line AB. That looks complicated on paper.
It does, but let's just translate that into plain English. That equation is just saying the output is 1 if A is true and DB is false, or if A is false and DB is true.
So, one or the other, but not both.
Exactly. It's the condition of exclusion.
Yeah.
And for the exclusive NOR, the equation is by cos AB plus overline B.
Okay, so that means the output is 1 if both A and B are true, or if both A and B are false.
The condition of equality. Understanding these derived functions is really where the whole optimization game begins.
Speaking of optimization, let's get right into the goal of this entire deep dive: simplification. The application of Boolean theorems. Why do we need these rules?
Because every single tool in this mathematical toolkit, every Boolean theorem, is designed for one thing: to reduce the complexity of the expression.
And why reduce complexity?
Because complexity translates directly into physical gates, which means it translates into power consumption and time delay.
Let's talk about the master tool of manipulation here, De Morgan's theorems. These seem central to rewriting and simplifying expressions.
Oh, they're phenomenal. De Morgan's gives an engineer the power to swap between different logic types while keeping the function exactly the same.
What's the rule?
It states that if you complement a product of variables, it's the same as the sum of the complements. So overline x plus y becomes overline x plus overline y.
And the other way around.
The complement of a sum is the product of the complements. Overline x plus y becomes overline y.
Okay, hold on. If I use that rule, doesn't that just add more not eats to my system? I mean, how does swapping one complex NAND gate for 3 separate AND and NOT gates simplify anything?
That is a great question, and it really highlights the hidden utility here. Sometimes the goal isn't just to reduce the total gate count.
Oh.
It might be to change the type of gate you're using. Or, more often, You change the form of the equation so that other simplification theorems can then be applied. It's like algebraic positioning, setting yourself up for the biggest win later on.
I see. So let's get to that big win. What's the bottom line? Why do companies invest millions in engineers who are just brilliant at simplifying these equations?
The hardware implications are the real aha moment. Mathematical simplification directly reduces the circuitry you need.
Smaller circuit size.
Right. Less silicon chip area, fewer physical components, and lower power consumption. All of that means cheaper fabrication and a smaller final product.
But the crucial gain, the one we all care about as users of technology, has to be speed.
Absolutely. Speed is everything. When you simplify the logic pass, you are shortening the propagation delay.
The signal latency.
Exactly. Think of it like this. If a signal has to travel through 5 different gates, each one adds a tiny delay. But if you can simplify the function and reduce that path to just 2 gates, you've instantly made that operation faster.
And simpler circuits are also more reliable, I'd imagine.
Far more.
Yeah.
And easier to test.
It's wild to think that a pencil and paper exercise translates directly to billions of dollars saved and microseconds gained in hardware.
It really does. Take a simple expression like 6 axles plus overline xy.
Okay.
Using a basic Boolean theorem, that entire function simplifies to just 6 axles plus y.
Wow.
So think about the hardware. The original version needed an inverter for the overline, an A and D gate, and then an OR gate. 3 components.
And the simplified one.
Just a single OR gate. That one algebraic step removed 2 physical components and shortened the signal path. That's a huge deal.
That's incredibly persuasive. Okay, now before we get to the most powerful simplification tool, the K-map we have, to be able to describe the function we're trying to simplify in the first place, we need the truth table.
The truth table is the absolute foundation. It's the static, exhaustive description of what the circuit does.
A table that shows how the output depends on every possible combination of inputs.
Every single one. And for any function with n inputs, there have to be 2 LO rows in that table to cover all possibilities.
So once we have that table, how do we get the actual function from it?
It's surprisingly straightforward, actually. You look at the table, and you only care about the rows that produce a logic 1 output. You could ignore all the zeros.
Okay, just focus on the ones.
Right. Then you convert each of those 1 rows into a product term, and you just sum them all together. This gives you an equation in what's called the sum of product, or SOP form.
And each of those individual product terms has its own name, right?
Yes, we call them min terms. So a term like overline BCY is a min term. And when engineers want to describe a function quickly, they use a shorthand called canonical form.
The one with the sigma symbol?
Exactly. You'll see it written as sigma MMA, and then just a list of the min term numbers that result in a 1 output, like sigma M3, 4, 5, 6, 7, and it's very concise.
So the truth table gives us this static map. But digital systems are dynamic, they're always changing. That's where the timing diagram comes in.
Correct. The timing diagram is the dynamic view. It's a graph of voltage versus time. It's absolutely essential for seeing how signals change and for showing the timing relationships between multiple signals. It's where you can actually see that propagation delay we talked about.
Okay, so now we have our equation, but it's still in that big, complex SOP form we got from the table. We need to simplify it visually. Let's introduce the engineer's secret weapon, the Karnaugh map.
The K-map is just a genius piece of geometry married to algebra. It's a visual mapping tool. It's like a truth table, but it's arranged in a very specific way to exploit patterns for simplification.
So each little box or cell on the map represents one of the min terms.
1 for each possible min term. So for 4 variables, you get a map with 16 cells.
And the genius isn't just the layout, it's the specific ordering of those cells.
That is the critical part. The map is ordered using something called gray code logic. And what that means is that the min terms in adjacent cells, whether they're touching horizontally, vertically, or even if they wrap around the edges.
They wrap around.
Oh yeah, the map is like a torus. And those adjacent cells are designed to be different by changing 1 variable only.
I see. And that's the key to the whole thing.
That's the foundation for the simplification.
So once we plot all our ones onto this special map, what are the rules for grouping them to simplify?
The goal is simple. Cover all the ones with the largest possible groups, using the fewest number of groups.
And the groups have to be a certain size.
They do. They must be rectangular, and their size has to be a power of 2. So 2 cells, 4 cells, 8, 16.
And they could overlap.
They can, and they often should overlap.
Yeah.
It's often necessary to make sure you're creating the largest possible group for a given one, even if that one is already part of another group.
And the bigger the group, the more simplification you get.
Exactly. Every time you double the size of a group, you eliminate one variable from the resulting simplified term.
That seems like a really fun strategic puzzle. But there's one more trick, isn't there? Something to maximize the simplification even further. Don't care terms.
Don't care terms, you'll see them marked X or D on the map, are vital in the real world. They come up because, in practical designs, some input combinations might be logically impossible.
Or they just never get used.
Right. Like if you're using 4 bits to encode a decimal digit, BCD, you only use the codes for 0 through 9.
So the inputs that would represent 10 through 15 are unused. They'll never happen.
Never. So you don't care what the output would be for those combinations. This is where the strategic power comes in, because you get to choose.
You treat them as whatever helps you the most.
Precisely. You can treat a don't care term as a 1 if it helps you form a much larger group.
Which gives you a simpler term.
Or you can treat it as a mo1 and just ignore it if it doesn't help. By leveraging these X's, you can achieve a level of simplification that just using algebra would probably miss. You get the most efficient, fastest hardware possible.
Incredible. It moves from abstract math to this highly visual, strategic optimization. So now that we understand simplification, let's look at the physical components that use this logic, starting with universal gates.
We're talking about NAND and NOR gates. They're called universal gates because mathematically, any Boolean function, no matter how complex, can be built using only NAND gates.
Or only NOR gates.
Or only NOR gates.
Why is that so important in the industry? Why stick to just one gate type?
It's a huge optimization choice for manufacturing. Using a single type of integrated circuit, or IC, simplifies the whole production line. It reduces inventory and it standardizes testing. It's about efficiency of scale, not just the raw gate count on one chip.
Makes sense. Now, beyond individual gates, engineers use prepackaged complex logic blocks, these medium-scale integration or MSI packages. Let's run through the most common ones.
Okay, let's start with a decoder. Think of it as a translator. It takes n inputs and gives you up to 2 null outputs. It interprets an input code and makes sure only one specific output line becomes active.
You mentioned the BCD example earlier. That's a classic application.
Perfect example. The BCD to 7-segment LED display decoder. The input is a 4-bit code for the number, say, 3 code. The decoder figures out exactly which 7 LED segments need to light up to display that digit. It translates code into physical action.
And its opposite is the encoder.
Right. The encoder reverses that. If you press one of 8 buttons on a keypad, an 8-to-3 encoder sees which single line was activated and converts that back into a concise 3-bit binary code.
Okay, next up we have the one that acts like an electronic switch, directing data traffic. The multiplexer, or MUX.
The MUX is also called a data selector. It's a logic circuit that takes data from several input lines and routes it to a single output line.
And how does it choose which one to send through?
It's controlled by dedicated selection inputs. It's like a switchboard operator, picking one stream out of many. A 4-to-1 MUX is a common one.
And finally, to complete the pair, the reverse of that is the demultiplexer, or DMUX.
The DMUX takes a single input stream and connects it to one of several possible output lines. Again, the selection inputs control where the data goes. It's a data router.
So that gives us a really comprehensive picture. We've gone from the basic math of Boolean algebra and De Morgan's to the visual strategy of truth tables and K-maps, and finally to these sophisticated pre-built blocks that run modern hardware.
You know, these tools might seem abstract, but they are the entire reason your tiny laptop performs calculations faster than supercomputers from 50 years ago.
It's all about that pursuit of the simplest, most elegant logic expression.
Which reduces power, shortens propagation delay, and makes these devices incredibly cheap and reliable.
Every time an engineer uses a K-map to find a clever grouping that shrinks an equation, they are directly impacting the physical nature of our digital world. They're shaving off nanoseconds and saving component costs.
It's the art of efficiency at the deepest level of design. So the next time you marvel at a speedy, tiny electronic device, remember you are seeing the direct result of an engineer mastering this power of simplification.
And we focus this entire time on combinational logic, where the output is based only on the current input. It's completely stateless.
Which, it naturally leads us to a fascinating question for you to think about.
Yeah.
What happens when the system needs persistence? What kind of logic circuit is required when the output must depend on past actions or historical states? What enables a digital system to remember?
We'll have to leave that element of memory for another deep dive. Thank you for joining us.